Hi, I'm Chem's best friend. I make chemistry easy. I'm a graduate of MIT, and I have more than 17 years of experience teaching AP chemistry and chemistry classes. Please like and subscribe to my channel. And if you are interested in private tutoring lessons, the information is on the screen. Hi, are you ready to do some solution stoichiometry today? We will be doing a lot of number crunching and review a little bit about solutions. So let's get started. Let's go and do this reaction. I hope you remember it. Potassium iodide with lead 2 nitrate. We're going to mix it. And few things to keep in mind. Let's write few things. Number one, I hope you know limiting reactants. Limiting reactants. Yes, they are coming back and we will be using them today. And the second thing is our molarity calculations. So remember, big M molarity is moles of solute per liter of solution. So that means moles will equal molarity times liters. Keep that in mind. That will be very, very important. Okay, so let's get going with this reaction. Let's rewrite this. Here it is. And what type of reaction is it? So you have an ionic compound mixed with another ionic compound, two solutions. It's our double replacement reactions. Yes, we're going to switch our cations. So lead will go with iodine and potassium will go with nitrate. That's our first step. Second step is we're going to now make our compounds neutral. Well, lead is 2 plus, iodide is -1, so we need 2 of them. And here potassium +1, nitrate -1, we are good. We're going to balance our reaction. We need 2 right here and we need 2 right here. And we're going to look at our solubility rules to determine what is the solid, what's AQ. And this lead to iodide will be solid. Potassium nitrate will be AQ. Okay, this is our setup. We're going to get 100 milliliters of potassium iodide solution, and it will be 1.35 molar. And we are mixing it with 75 milliliters of 1.20 molar lead to nitrate solution. And the question is, how many grams of my solid will I form? And anything that's left over, what's the molarity of my ions left over swimming? So I think the best way to do this is to do a rice table. And R, so this is R will stand for our reaction. I will be initial amount. C is for change. And E is for my end. So can you remember that? Okay, how did we solve limiting reactants problems? We first determined limiting reactant, and then we used the limiting reactant to determine how much product is going to be made. So we have to first determine limiting reactant, but the issue is we need to change everything to moles. Once I change things to moles, I will be good to go. So really fast, do you remember? Moles, MOL, is molarity times liters. Keep that in mind. So we have things in milliliters, we will need to change it to liters. So if you're going to do 1.35 molar times 0.100 liters, we are going to have initially 0.135 moles of potassium iodide solution. And if we do 1.20 molar times 0.075 liters, we are going to have 0.0900 moles of lead to nitrate. Okay, now we have to determine our limiting reactant. So I need you to look here. I have a 2 to 1. There's 1 here. Yes, it's implied. I have a 2 to 1 mole to mole ratio. And that means that for every 1 mole of lead 2 nitrate, I'm going to use up 2 moles of potassium iodide. So that means if I have 0.09 moles of lead nitrate, I need double that of potassium iodide. Now, let's compare. Do I have double that amount? No. If it was double, I need 0.180. But I have less. I have 0.135. So that means my potassium iodide is my limiting reactant right there. That's my limiting reactant. And here I have excess. Okay. So remember definition of limiting reactant. I will use all of it. So in the end, I'm going to have 0, right? So now, for every 2 potassium iodide, I'm going to 2 moles, I'm going to lose 1 more. So I'm going to say this is like, for every, this will be reacting, this will be going down 2 times, while this is going down 1 time. And this will be 1 mole will appear for every 2 moles. I'm looking at my stoichiometry here. And I'm starting at the beginning with 0 and 0 here too also. Okay, so if 0.135 minus 2x is 0, right? 0.135 minus 2x is 0. So this will be minus 0.135 moles. But my x, yes, 0.135 minus 2x is 0. My x will then be minus 0.0675 moles. That's my x then. And if I'm going to go down, here is plus x. Now I'm going to add that amount, 0.00675 moles. And I'm going to also now plus 2x, and remember what my 2x is. My 2x is 0.135 moles. Do you see how you can do things really fast using a table? I think it's much easier to see. So if we do some numbers in the calculator, I'm going to be left with 0.0225 moles of my lead to nitrate. I'm going to make 0.0675 moles of a solid, yes, lead to iodide, and I'm going to also have 0.135 moles of potassium nitrate. Okay, the question is how much solid I'm going to make. Well, I have this many moles. Let's take the moles, change them to grams. So let's keep going with some calculations here. So I'm going to have 0.0675 moles of my solid. And I'm going to look at my periodic table and add up things to get my molar mass. And that's 461 grams of lead to iodide per 1 mole of lead to iodide. And I plug this into a calculator and I'm going to get 31.1 grams of solid will be made. Okay. That's great, but now let's look at the ions, which are still swimming in a solution, which are left over. What is left over? Let's look at that here. Well, I'm going to have right here, part of this solution, right here will be left over. This is my solid, and I'm going to have right here potassium nitrate. Potassium nitrate made. Now, keep in mind, what are my spectator ions? Do you remember my spectator ions? Maybe we should highlight them. My spectator ions are, well, this is my AQ. So my spectator ions are potassium and nitrate. Potassium and nitrate. They were just swimming around in a solution at the beginning, and they are swimming after. Did their concentration change? It did not. So let's go and double check with our math. So I'm going to rewrite that I have this much amount. Whoops. Let's go back here. I have this much amount of the solution of moles, and I have this much amount of my solute in this solution. Let's rewrite this and let's do some calculations. So I have, what's left over? I have 0.0225 moles of lead to nitrate, and then I have 0.135 moles of potassium nitrate. Now, what does lead to nitrate mean? It will split up into 3 ions, yes? It will split up into lead 2 ion and 2 nitrates. So that means I am going to split this up, and I'm going to have 0.0225 moles of lead swimming, yes, lead ions, but I'm going to have double that amount because I have 2 over here, this 2. That means I have double that amount of nitrate swimming. So I am going to take this number, multiply by 2, and I'm going to have 0.045 moles of nitrate swimming. Yes, let's do the same thing here, but here is just 1 to 1. So I'm going to have 0.135 moles of nitrate swimming, and I'm going to have 0.135 moles of potassium ion swimming. Now have a look here. This nitrate we can add up, because this is this and this swimming. We're putting everything in one big beaker. I have 0.180 moles of nitrate together. 0.180 moles of nitrate and 0.135 moles of potassium. Let's go back here. Look at this. I have this many moles of lead to nitrate. And for every 1 mole of my compound, I have 2 moles of nitrate, right? How many moles of nitrate did I have at the beginning? Take this number, multiply by 2, 0.180 moles. Yes? Oh my gosh, it's the same number. It's my spectator ions. They were swimming there before, they are swimming there after. Their concentration did not change. And what about potassium? How much did I have? I have this many moles of potassium ion swimming. How much do I have after? Same number. Isn't that great? You can double check. And I do not have the same amount of lead because some of the lead was used to make solid. So this is the leftover, the excess lead, right? There is no iodide left because potassium iodide was my limiting reactant, and all iodide ions were used up to make the solid. Okay, so I have this many moles swimming, and remember my molarity, just really remind quick, molarity equals moles per liter. So if I want to know my molarity of each separate ion, so lead, I'm going to have 0.0225 moles swimming in, well, what's the volume? What's the volume? Remember, I had 100 milliliters in one beaker, and they were added to 75 milliliters in another beaker, right? So I have 175 milliliters total, which is 0.175 liters, and we stick this in a calculator, and we get that we have 0.129 molar for lead. Let's do the same thing with potassium. Potassium ions, well, we have 0.135 moles of potassium ions over 0.175 liters, and that gives us 0.771 molar. And last but not least, let's do nitrate. Again, how many we have? We have 0.180 moles over 0.175 liters. And we plug this in, and we will have 1.03 molar for nitrate. And why don't we do that same thing for lead iodide? Because this is a solid, right? This is a solid. It will be solid on the bottom. So this is my solid. So I do not do that. Is this making sense? Are you ready to try one more? Let's try a different example. One more problem. So here we have our magnesium ribbon stuck into some hydrochloric acid solution. And let's come up with what is my product. So what type of a reaction is this? Do you remember? Single replacement reaction. So what will switch places with what? We check our activity series. And magnesium above hydrogen. Magnesium wants to be ionic. Hydrogen wants to be neutral. So magnesium and hydrogen will switch places, yes? And we will make magnesium chloride. But magnesium is +2 charge. Chlorine is -1. And solubility rules, this will be AQ. Plus we're going to make H2, remember diatomic gas. We have to balance this. So we're going to put 2 right here. And here is our balanced reaction. Let's do this setup. We're going to put 0.80 grams of magnesium ribbon into 15 milliliters of 3 molar solution of hydrochloric acid. And the question is, how many milliliters of gas will we produce at STP? How is that? So we're going to do again our RICE table. R stands for reaction. We wrote our chemical reaction. I is my initial concentrations, yes, or initial amounts. This absolutely can be moles, initial amounts. Moles, C is for change, and E is for end. How much amount do I have at the end? We're going to change everything to moles. Change everything to moles. And this one, magnesium, we will use our molar mass. And this one, remember, what does moles equal? Moles equals molarity times liters. So let's do some number crunching. For magnesium, if I have 0.80 grams of magnesium, I look at my periodic table. Yes, and I see molar mass. 1 mole of magnesium is 24.3 grams. I plug this in and I'm going to have it. I have 0.033 moles of magnesium. Yes, so let's write this on our table. So I have 0.033 moles. Now let's find out how many moles of hydrochloric acid we have. So molarity, 3.0 times 0.015, right? We have to change the milliliters to liters. And we're going to have it, we have 0.045 moles. And at the beginning, we have 0 and 0 here. Okay, so let's look our stoichiometry. What does that mean? What's going on here? For 1 mole of magnesium, I need 2 moles of hydrochloric acid. 1 mole of magnesium, 2 moles of hydrochloric acid, yes? So for this amount, 0.033 moles of magnesium, I need 0.066 moles of hydrochloric acid. And I look and I have less. I have less than I need. So therefore, my limiting reactant is my hydrochloric acid, and I'm going to have excess magnesium. That means some magnesium ribbon will be left over. Some magnesium ribbon will be left over in my test tube. And for every 1 mole of magnesium that is used up, 2 moles of hydrochloric acid are used up. 1 mole of magnesium chloride, yes, is made, and 1 mole of H2 gas, hydrogen gas, is made. So this will be my ratios, -x minus 2x plus x plus x. Limiting reactant, by definition, is going to be all used up. So I'm going to end up with 0. So this will be minus 0.045 moles. Okay, so 0.045 minus 2x equals 0. That means my x is, this will be 0.0225 moles. That's my x. So that means this will be plus 0.0225 moles. And this will be plus 0.0225 moles. Okay, well, that's easy for right here, 0.0225 moles. And plus, oops, this is not plus, it's just that amount here. So this is 0.0225 moles. All right, and a calculator quickly subtract the two numbers. I'm going to have 0.0105 moles of magnesium ribbon left over. Okay, so let's figure out, now that we know moles of my gas, yes, I can quickly figure out volume. So right here, if I have 0.0225 moles of hydrogen gas made, remember our conversion factor? There is 22.4 liters of any gas per 1 mole at STP, at standard temperature and pressure, and I have to change it to milliliters. The question asked me per milliliters. So I'm going to punch the numbers in a calculator, and you're going to get 504 milliliters of H2 gas will be made. Okay, what's the molarity of my solution that will be left over? And also, how much magnesium ribbon will be left over? Let's think about everything. So this is the amount of magnesium ribbon that will be left over. I can change it to grams, and I can subtract, yes? So if we have 0.0105 moles of magnesium, and this is now we're going to do 24.3 grams of magnesium per 1 mole. Yes, we're going to have then 0.255 grams of magnesium ribbon left over. So here is what I have left over. This is what right there. This is what's end, and I can change it, and right here I have my grams. And then I can figure out the molarity of my solution. So I have 0.0225 moles of magnesium chloride solution, and the volume is 15 milliliters. And I have 1.5 molar solution of magnesium chloride. And there it is. How did you do? Could you follow me? I hope so. So I hope that you learned how to do a rice table, reactant, initial amount in moles, change, and the end amount. And you can clearly see everything in front of you. You can pick your limiting reactant, and then off you go. Thanks for watching, and see you next time.